Hello everyone, welcome to a brand new series where we'll be taking on a real challenge, building our own TCP communication layer completely from scratch. No shortcuts, no pre-built frameworks, just raw sockets and C++. Now you've probably heard of libraries such as BoostAsio. They're powerful, but have you ever wondered what's really happening under the hood? That's exactly what we'll explore together in this series. We'll start simple by creating a socket and building a blocking TCP server that can accept a connection and exchange messages. Once the basics are clear, we'll level up to an asynchronous server with a connection manager that can handle multiple clients at once. From there, we'll move on, adding a TCP, an HTTP server and client, and eventually WebSockets. I also plan a surprise app that will run entirely on our custom communication layer. So why not just use BoostAsio? Because knowing the internals gives you control. Real-world projects often demand optimizations or features you won't find in off-the-shelf libraries. By writing everything ourselves, we gain that deeper understanding. Later on, we'll even re-implement parts using BoostAsio to compare design and usability. And since we live in the age of AI, we'll test how AI-generated code can open new possibilities. We'll look where it helps, where it goes wrong, and how to fix it. If you ever wanted to truly understand how networking works from raw sockets all the way to the servers, clients, HTTP, and beyond, this series is for you. Let's get started. When we open a socket, there are a few steps we need to go through in order to establish a TCP connection. On the server side, the process starts by creating a socket, then binding it to an address and port. After that, the server begins listening for incoming connections. Once the client attempts to connect, the server accepts it, which creates a brand new socket dedicating to communicating with that client. Only at this point can data actually be exchanged, and it's important to note that this happens on a different socket than the one used for listening. On the client side, things are much simpler. The client just creates a socket and connects it to the server. If the connection succeeds, it can immediately start sending and receiving data through that same socket. I'm using almost the same setup as before. The project is built with CMake and I've set up a Conan to manage dependencies for a simple Conan file.py. At this stage, we don't actually need Conan to install anything since there are no external packages required yet. But later, when we bring in the Boost library, this setup will save us time and make the whole process much smoother. This is how I handle the dependencies. I create a build folder, then run the Conan command inside it. I usually type the commands manually, but I also keep them in a bat file for convenience. Let's kick things off with the basics. We'll create a socket that listens for incoming connections, accepts them, and then exchanges a few messages with that client. In other words, we're building the simplest possible TCP server. To test it out, I've already prepared a small Node.js TCP client and I've included all the necessary headers in the project so we can jump straight in. Now a quick note on my setup. Over the past few months, I switched from my main development environment to Windows, so this project is running there. The good news is that socket programming on Windows is almost identical to Linux. The functions look nearly the same with just a few small differences, and I'll point those out as we go. If there is enough interest, I might put together another video showing how to write the project in a fully portable way. And here's a fun side note. Tools like Cursor can actually help port projects across platforms in minutes. It's a great example of how AI can save time on the boring part so we can focus on the fun stuff. First, we need to initialize the WinSock DLL by calling WSA startup. This step is required only on Windows. On Linux, you don't need WSA startup at the beginning or WSA cleanup at the end. These functions are Windows specific. Once WinSock is initialized, the next step is to create our socket. A socket is basically an endpoint for two-way communication. It can link two machines over a network or even two processes running on the same computer. Each socket is defined by three things: an IP address which identifies the host, a port number which identifies the specific service or application, and a protocol which determines how the data is transmitted, such as TCP or UDP. For this project, we'll be using TCP. To set that up, we specify a few parameters when creating the socket. AF_INET tells the system we are working with IPv4, or if we said AF_INET6 if we wanted to IPv6. SOCKSTREAM indicates that we want a TCP connection, whereas SOCK_DGRAM would be used for UDP. Finally, we usually pass 0 for the protocol, which lets the operating system choose the appropriate default, like TCP IP. If the socket creation fails, the function returns invalid socket, which is just -1. Otherwise, it gives us a valid socket handle that we can start using. For this project, I set the host address to localhost 127.0.0.1 and the port to 12,301. The next step is to configure some socket options. These options can be applied at different levels, at the generic socket level, at the TCP level, or for IP level, IPv4 or IPv6. One option I almost always set is SO_reuse ADDR. This tells the operating system that it's allowed to quickly reuse the same address if the connection gets interrupted. For servers, this is especially important. If a connection breaks, we don't want to wait before using the same address and port, otherwise we risk downtime. For TCP clients, though, this option isn't nearly as critical. Before we can move on, our socket needs a SOCKADDR object. As mentioned earlier, every socket is defined by an address and a port, and most of these functions will be calling from here on out require this object. The SOCKADDR type itself is just a generic structure that can hold socket information. In practice though, we almost never use it directly. Instead, we rely on more specific types: SOCKADDR_IN for IPv4, SOCKADDR_IN6 for IPv6 and socketddr_un for Unix domain sockets. Now we simply generate the socketddr object from our host address and port. Once we have it, the next step is to bind the socket. Binding associates a local address and port with the socket, essentially telling the operating system this socket will listen here. I also create a small error printing helper that retrieves the last error code whenever an operation fails and prints it in a readable way. It makes debugging much easier while working with sockets. After binding the socket to an address and port, the next step is to put into listening mode. This is where things get interesting because we can handle connections in two different ways. Synchronous or blocking, the thread pauses and waits until a connection is detected. Asynchronous or non-blocking, the thread keeps running and incoming connections are handled later without stopping execution. When a client tries to connect, the operating system places the request into a queue. The second parameter of the listen function defines the maximum number of connections in the queue before they start getting declined. In the non-blocking case, we can do other things and retrieve a connection at a later point when we want. For this first example, we go with the blocking approach. The server will simply wait until a client connects. We will explore the non-blocking or the asynchronous case in the next video. To accept a connection, we call the accept function. This pulls one request off the queue and returns a new socket dedicated to that client. From this point on, we use that new socket to send and receive data. Once we've got a valid socket, we can immediately start exchanging messages. In this example, I start a separate thread that listens for incoming data from the client using regv. After receiving a message, the server replies with confirmation using send function. The regv function tells us how many bytes were received. If something goes wrong, it signals an error, and if the connection is closed, it simply returns 0. On Windows, you can dig into the exact error details using WSA getLastError, while on Linux, one would use error to retrieve the error. I also set up a polylisten feature so the thread runs as long as the connection is active, and I can track when it finishes, specifically when the client closes the connection. This gives me a clean way to know when the send-receive thread has ended. If I want to stop earlier, I added a check inside the while loop to see if the Q key was pressed. Doing this in a non-blocking way isn't straightforward with standard C++, so I used a platform-specific approach by including the conio header for the keyboard hit and get character functions. Finally, when either the client disconnects or the Q key is pressed, the program shuts down gracefully. The thread is stopped, all sockets are closed, and WSA cleanup is called to release the resources. Here is a simple JS app with which I can test my blocking C++ server. It creates a client that tries to connect to the host on 127.0.0.1 and the port 12,003.1. It reacts on data received, close, and error. It also has a prompt where we can enter messages to send them. Now let's test this app is working. So WinSock was initialized, we're waiting for a connection on socket 264. I'm printing. Let's test using this one. So we connect it. We see that we are starting to read from a different socket from 272. If we enter a message, we should receive it on the other side. Or I can print also how are you again. Now if I say exit, this send the message. Now I get the connection closed and the whole application stops. I can start it again here. Now I'm waiting for a connection on another socket. I connect using the JS application. I can send another message. I want you to stop. And I get the message from the client, I want you to stop. I press the Q key, I'm exiting, and basically then also the Node.js stops because the socket was closed from the other side. So yeah, basically this was it. Thank you for watching to the end, and this is only the beginning. We simply made it possible for a few messages to be exchanged as first step along the journey. As usual, please leave in the comments what you liked in this video or how it can be improved. Don't forget to like and subscribe. I will go further with this challenge in the next video. Thank you very much again and see you in the next one.